Hi, welcome back. This is still Ken and we're still on our course on mechanics and this is lesson 5, applying Newton's laws. In the previous video, we applied your Newton's first law for particles in equilibrium. In this video, we are going to continue with our discussion and we are now going to consider systems which are accelerating. We begin with our lesson on the dynamics of particles. In the previous lesson, we have applied your Newton's first law to bodies which are in equilibrium. That is, these are bodies which are either at rest or moving at constant velocity. In this lesson, we are going to use Newton's second law to bodies in which the net force is not zero. These bodies are not in equilibrium and hence are accelerating. And we usually call these problems as your dynamics problems. If that's the case, then we're going to apply your Newton's second law, that is the sum of all your net force F is equal to your mass times your acceleration. And since your force and then your acceleration are vector quantities, we have the individual components, that is the sum of all your Fx is equal to your mass times acceleration along the x-axis, and the sum of all your Fy, that is equal to your mass times acceleration along the y-axis, and the sum of all your Fz, that is equal to your mass times acceleration along the z-axis. We're going to use these equations to the problems in the next slide. And by the way, we're still going to use the same strategies that we have applied in particles in equilibrium in solving problems which are now accelerating. Let's have an example. This is about weighing a fish in an elevator. Consider yourself as, or let's say you're a fish vendor, and then you want to sell your fish in a crazy idea, like say for example, selling the fish in an elevator. Let's say you're selling the fish in a condominium, and of course the condominium has an elevator, and then you sell your fishes there. But you take note that your elevator, it moves upward and it goes downward. Okay, now for the problem. A person weighs a fish of mass m on a spring scale attached to the ceiling of an elevator. A spring scale is something that you usually see in the wet market. For the problems, show that if the elevator accelerates either upward or downward, the spring scale gives a reading that is different from the weight of the fish. In short, does the movement of the elevator changes the way that your fish weighs on your spring scale? So that is your first problem. The second problem is evaluate the scale readings for a 40 Newton fish if the elevator moves with an acceleration along the y-axis of plus and minus 2 meters per second squared. And lastly, suppose that the elevator cable breaks and the elevator and its contents are in free fall. What happens to the reading on the scale? So let's solve this one. For the first problem, show that if the elevator accelerates either upward or downward, the spring scale gives a reading that is different from the weight of the fish. So for solving this one, again, our first strategy is always to draw the free body diagrams of the system. And on the figure to the left, we already have your free body diagram, and we are taking the fish as our body. So for that, we have a tension that is upward exerted by your weighing scale, and then we have your weight of the fish, which is downwards. That is your mass times your gravity. So from that free body diagram, we write your equations of motion. The equations of motion again is applied to the fish. So these are just all along the y-axis. So we have the sum of all your forces along the y is equal to your tension, which is positive since it is upward. And then you have your weight plus the negative of mg. So it's tension minus mg. And then this is equal to your mass times acceleration along the y. So this time now we have your acceleration along the y-axis since your body is accelerating with the elevator. Okay, if you're some are actually wondering what happens for the sum along the x. So for the sum along the x, just for a while, for the sum along the x, we have the sum of all your fx, that is just 0, since there is no force that is involved along the x-axis. Otherwise, if there is one, then your fish is also accelerating along the x-axis while it moves downward. But since this is a purely a vertical problem, you only have your forces along the y-axis. Now again, we have your sum of all your Fy is equal to your tension minus mg, that is equal to your mass times acceleration along the y-axis. And here we have chosen upward as the positive direction. So when your elevator goes upward, we have positive ay, and then when it goes downwards, you have your negative ay. From the equation of motion, let us solve for t. Let us solve for the tension. The tension here is what is given by the weighing scale. Your weighing scale contains springs, and those springs are stretched or compressed, and that gives you the reading of your weight. So for that, we are going to solve for the tension T. So that is just your from your equation of motion. So your T now is equal to your mass times acceleration along the y minus your mg. So we just move your mg term to the right. So you have T is equal to may plus mg. And taking out mg in the term, we have mg times ay over g plus 1. And since your mg is just your force due to your gravity, so we have we just replace it with fg, and then ay over g plus 1. So that is the tension in your weighing scale, or on your spring balance. So what do we get here? Okay, looking at this term here, okay, when we have positive ay, the scale reading T is greater than the fish weight mg if acceleration is upward. So as you can see here, if your ay is positive, it adds, then it is divided by your g. It just add a quantity or a ratio to, it just adds some value to your plus 1. Okay, so your weight, which is given by your fg, multiplied by this quantity here, makes your weight mg a little greater, or greater than the normal weight of the fish. What happens if you have a negative ay, that is your elevator goes downwards? So if that is the case, the scale reading is less than mg if acceleration is downwards. What happens if you have your ay is negative? So you have this term here as negative plus 1, okay? And then you multiply that 1 to the normal weight of the fish, which is fg. So that is a little lesser than the normal fish, the normal weight of the fish. That is what you actually observe when you're riding an elevator, and then the elevator suddenly moves upward. So you'd feel that you're actually being pushed downwards. And if you're going to take the reading of your weight while, let's say you're standing on a weighing scale, and then you're riding an elevator, and then the elevator moves upward, you feel that push within, or that push downward. And if you're going to weigh yourself, you'll see that you're actually weighing more when the elevator moves upward. And if still in the same situation, and then you are riding the elevator standing on the weighing scale, but this time your weighing scale moves downwards, you'll feel that you're weighing a little less, or you feel that how to call this, in in our diet, you feel that nabili ng imong kalag when the elevator goes downwards. So you'll weigh a little less than your normal weight. So what can you get here? So when you're going to sell the fish, it's either you sell the fish when the elevator is stationary, you get the normal reading, or you sell the fish when the elevator moves upward. But if you're the one that is buying the fish, you only buy the fish when the elevator is stationary, or either when the elevator goes downwards, because as you can see, when the elevator goes downwards, the fish weighs less, so you'll pay less. So don't buy the fish when the elevator goes upward, because it weighs more, so you'll pay more. But if you're the seller of the fish, you only sell the fish when the elevator goes upward. You'll gain more interest from that. But of course, it's a bad idea. Okay, you can actually try it when one time when you're going to ride the elevator and you feel it. Try to feel the elevator when it goes upward, and try to feel it when it goes downwards, and you'll feel the difference in riding the elevator. Let's proceed to the next problem. Evaluate the scale readings for a 40 Newton fish if the elevator moves with an acceleration AY plus minus 2 meters per second. This is just, we're just actually going to verify here if it is indeed true that when the elevator moves upward with a positive acceleration, the fish weighs more, and if the elevator goes downwards, the fish weighs less. So in this problem here, we have this 40 Newton fish as your FG. This is the weight of the fish, and then you have your acceleration AY. We either have plus 2 meters per second squared or negative 2 meters per second squared. If A is upward, you have plus 2 meters per second squared. And from the equation that we have derived for the tension, so we have, again, this is just your tension. From the previous slide, you have your tension is equal to your FG times your AY over G plus 1. Okay, so that is the reading on the spring balance. So your tension is equal to 40 newtons times 2 meters per second squared divided by 9.8 meters per second squared. Your units just cancel out, so plus 1, and you get a reading of 48.2 newtons. So as you can see, the fish here weighs plus 8.2 more than its normal weight when the elevator is stationary. If, on the other hand, the acceleration is downward, that is, we have your negative 2 meters per second squared, the tension is equal to 31.8 newtons. So it weighs a little less than 40 newtons when your elevator is going downwards. So if you're going to sell the fish while the elevator moves downward, you'll see that you have a lot of loss. Okay, and if you're going to sell the fish when the elevator goes upward, you'll gain more interest. So tip, if you buy a fish in an elevator, make sure that the fish is weighed while the elevator is either at rest or accelerating downward. But of course, nobody does selling fish on the elevator. But who guess? Or who can guess? Now, the last question, suppose that the elevator breaks and the elevator and its contents are in free fall, what happens to the reading on the scale? Okay, so again, suppose the elevator cable breaks and the elevator and its contents are in free fall, what happens to the reading on the scale? So if the elevator and the contents are in free fall, that means that your AY is equal to the negative G. So if that is equal to the negative G, so your tension here, that is equal to Fg times negative G over G plus 1. So this is negative 1 here. So you have negative 1 plus 1, that is 0. So your tension is equal to 0. So what you actually feel here, or what you actually observe here is, we call this one as apparent weightlessness. So it seems that your the weight of the fish is zero, so it weighs nothing. So it's called the apparent weightlessness. So the apparent weight and apparent weightlessness is actually what the astronauts feel when they are in space orbiting the Earth. Astronauts orbiting the Earth weigh a spacecraft feel or weightless because they have the same acceleration as their spacecraft, not because that they are outside the pull of the Earth's gravity. If no gravity acted on them, the astronaut and their spacecraft would remain in orbit but would fly off in deep space. So, um, orbiting satellites are still under the influence of gravity, and if there are astronauts there, like say for example in the space station, the astronauts are have the same acceleration as their spacecraft. So it seems like they are actually in free fall as it orbits around the Earth. So they're still under the influence of gravity, but they're accelerating uh, in the same direction, in the same magnitude with the spacecraft, and they're falling in circular paths as they are orbiting the Earth. And just some trivia or some question. As you can see here in the GIF image, this astronaut does not actually feel dizziness. So why can astronauts get dizzy in space? It's for you to find out. Let's have another example. So this is about an Atwood machine. When two objects of an equal mass are hung vertically over a frictionless pulley of negligible mass as in the figure shown here, the arrangement is called an Atwood machine. So what we have here in the figure is what you call an Atwood machine. The device is sometimes used in the laboratory to calculate the value of your acceleration due to gravity g. Determine the magnitude of the acceleration of the two objects and the tension in the lightweight cord. So here we're asked for the magnitude of the acceleration of the two objects and the tension in the lightweight cord. And also describe the motion of the system if the objects have equal masses, that is, if m1 is equal to m2. So let's solve the problem. So first we are asked to determine the magnitude of the acceleration of the two objects and the tension in the lightweight cord. So we have here your m1 that goes upwards and then, or accelerating upwards, and then your m2 accelerates downwards. We can think of this one as your m2 is weighs more heavier, or your m2 weighs heavier than your m1. So again, our first strategy is to draw the free body diagram. Always remember that one. Our strategy is to first draw the free body diagram of your system. Here we have two objects, m1 and m2. So m1 should have its own free body diagram, and m2 should also have its own free body diagram. So this is the free body diagram for your m1. The only forces acting in the system or in this body is the tension exerted by the cord and the pull of gravity, which is the weight of m1. So tension is upward, and then your weight is downwards. And you also include here the direction of the acceleration, which is upward. This is the free body diagram for your mass m2. Still, we have the tension that is upward and then the weight that is downward. So here, the acceleration is downward. So from this free body diagram, our second step in our strategy is to write the equations of motion. This is the equation of motion for m1. That is the sum of all your Fy is equal to your tension, which is positive. It is upward or exerted upward. And then plus the negative of your weight. So you have minus m1g. So you have your tension minus m1g, that is equal to your m1ay. Okay, so we have a positive acceleration, so you have m1ay. And this is the equation of motion for your m2. So you have the sum of all your Fy is equal to your tension minus m2g, that is equal to minus m2ay. Here you have a negative m2ay because our acceleration is downward. So we take here acceleration upward as positive and acceleration downward as negative. So again, we have here your two equations derived from your free body diagrams for M1 and M2. For M1, mass 1, you have the tension minus M1g is equal to M1ay. And for your mass 2, we have the tension minus M2g is equal to minus M2ay. Some question here raised is why is it that the tension for mass 1 and M2 is the same? So it's the same because your simple machine here, which is the pulley, actually just bends your system. So what we originally have is just a straight line interaction between your M1 and M2. So they're just connected by the same cord. Okay, so that's just the same tension, and your pulley, your simple machine, just bends your axis. Okay, it simply bends your axis. But again, whatever the tension M1 experiences or feels is the same tension that M2 experiences. So that's just the same tension T for both bodies. And we can now solve for the equation. That is by adding the two equations to eliminate your tension T. So if we do that, you have minus M1g plus M2g. That is equal to m1ay plus m2ay. Solving for the acceleration, you have your ay is equal to m2 minus m1 over m1 plus m2g. And you can verify that one from the equation above. And substituting this acceleration to equation 1, your equation 1, t is equal to m1g plus ay. Substituting ay to this term here, to this equation here, you have your tension T is equal to 2m1 m2 over m1 plus m2 over g. Okay, so that is the magnitude of your tension T. A question here is, by the way, you can also solve for T using equation 2, and you should also get the same answer because, again, as I've said earlier, whatever the tension that M1 experiences is the same tension that M2 experiences. So they get the same tension whether you use equation 1 or equation 2. But the question raised here is, or a problem we have here is, to describe the motion of the system if the objects have the same masses, that is, if M1 is equal to M2. What happens here? Now, if M1 is equal to M2, you see this term here, if they have the same values, it is equal to 0. And if that is equal to 0, your acceleration goes to 0. So if M1 and M2 have the same mass, your Atwood machine will not accelerate. So this will just be an equilibrium problem. Okay, so I have here an assignment for all of you, and this is for you to solve. This is about the acceleration of two objects connected by a cord. A ball of mass m1 50 kilograms and a block of mass m2 9 kilograms are attached by a lightweight cord that passes over a frictionless pulley of negligible mass as in the figure. The block lies on a frictionless incline of angle theta 30 degrees. Find the magnitude of the acceleration of the objects and the tension in the cord. So just a short discussion of the assignment for you to be guided. We have again two masses, M1 and M2. And for our strategy, each of these masses should have its own free body diagram. And from the free body diagram, you write your equations of motion. Just a short or just a rough illustration. We have here the forces your weight one, and then here your attention, and then here we have attention here. This should be directed here, and then you have your normal force at 90 degrees, and here always downwards is your always downward is your weight or your mass too. But you can extend this one to have your xy plane, and this one is equal to theta. So we have a rough schematic for your FBD for mass 1. So you have here your tension and then your weight 1. For M2, we have your normal force, and then to the left you have your tension, and then here is your weight 2. You can draw your xy plane. This is here your angle theta, and you can resolve this one. You have here your weight 2x, and then here you have your weight 2y. So I'm going to leave this one to you as your assignment. Hi, did you happen to be one of my students? And do you want to win a free prepaid load? Submit your assignments now. The first to submit the correct answer will win a 50 pesos worth of prepaid load. And submit your assignment using that JPEG or that PNG file by taking a clear picture of your assignment. You can also submit a .pdf file. Submit it using our UStep submission portal, and this is under assignment number 7. Again, the first to submit the correct answer will win the 50 pesos worth of prepaid load. And this is only valid until October 9, 2020, 8 p.m. only. Submissions after this time will not be anywhere considered for load. So what are you waiting for? Submit your assignments now. Good luck.